All right, we are the Georgia Tech team representing the Energy Club at Georgia Tech, and we were assigned to, of course, the Denver Auraria use case. Before we started, we just want to thank the organizers for their time in answering all our questions, as well as the judges for taking their time to listen to our presentation. So first we want to introduce the team. So myself, I'm Austin Fan. I'm a junior chemical engineer at Georgia Tech, and I was acting as a team organizer. We also had Katie Kang, who's a freshman chemical engineer, Jake Churchill, who's a sophomore mechanical engineer, and Matt Warner, a PhD candidate for chemical engineering. We also had advisors help us along the way. So we had Sam Talkington, Tyler Pillette, and Dr. Daniel Molzan. So first off, we wanted to talk a bit about the goals of our system. So Denver and the Auraria Sustainable Campus Program both have their very ambitious and very commendable sustainability initiatives. So it's, for example, Denver's 80 by 50 climate action plan, their 2030 100% renewable electricity goal, and Auraria's 5-year sustainability plan and their PV development roadmap are all very ambitious goals that not only show a great spirit and commitment, but also a definitive plan. But when we look at some of the progress, there's still a lot of progress to be made to hit those goals. So for example, Denver is at 1.2% of the 30 to 40% 2030 goal of solar electricity to go towards their renewable electricity. And Auraria has made very good progress so far in hitting 824 kilowatts of their 2,500 kilowatt goal by 2025. But as we can see, they just barely missed the 2020 goal. So that's where we wanted to make our system go. We want to help these districts catch up, meet, and exceed these ambitious goals laid out and really embody that spirit and commitment. And clean energy is only the base. We want to also help with their energy efficiency goals, greenhouse gas reductions, and improve community well-being from things like improved mental health or community building from these systems. We also want to hit the maximum system size to really help meet those goals as allowed by the constraints, including things like the conceptual constraints or financial constraints. And finally, we wanted to make this a unique, holistic community-based system with empirical and or social rationale to the 4 unique areas of the conceptual, financial, distribution system impact analysis, and the development plan. These images below are kind of the Auraria's icons to represent the goals of our system and how they intersect with their sustainable campus programs goals. Finally, we wanted to engage the Auraria higher education campus community, as it is a university campus, to help put these solar plans into reality. So Matt will go ahead and talk about the proposed system.
All right, so here are all the proposed systems for the Denver side. So all of these rooftops that you see were chosen because they have very few rooftop obstructions on them, and they have very little shading with respect to the other buildings around them. The section of the convention center was designed because it was well supported. It can support that load. And all of these rooftop designs were designed to produce the most energy per unit of roof area. If we go to the next slide, here are the proposed systems for Auraria. Auraria is a little bit different because there was a 25% behind the meter export constraint set by the utility. So with that said, all of the buildings were designed to meet that export constraint, not to go above. And each of these solar panel arrays were optimized for that. Now, the Confluence building and the Holly parking lot are 2 special cases, which Katie will go into a little bit further later on. Next slide. Okay, and so with the Auraria energy generation profile, this is a 2,798 kilowatt system on top of the 824 kilowatts that they already have, which will greatly exceed their 2025 goal based on our design. Next slide.
Yeah, so the team also focused on how we can target this design for the benefit of the community and the people as well. And we came up with the installation of agrivoltaics and a community garden on the green roof of the Confluence building. Since Denver has a semi-arid climate, the installation of agrivoltaics can really help save water and promote plant growth as well. As of today, there's only one other community garden, which is the Auraria Connect Community Garden. It was constructed by a local nonprofit called Denver Urban Gardens. And through another partnership with Denver Urban Gardens, we hope to add another garden through which more students can get directly involved with sustainability in their community. The garden can also be used as a great tool for community bonding, as a creative outlet for students, and volunteering as well. Another component that the team came up with was adding EV charging stations to carports, which would be located on the Holly parking lot, which is actually one of the largest parking lots on campus. So general benefits of carports are increased shading and also increased comfort for vehicles parked there. And by adding EV charging stations, we hope to also increase electric vehicle usage as well. Currently, there's only one other charging station on campus. So by adding more charging stations, we hope to make it more convenient and accessible for students.
So we also looked at some of the building energy efficiency benefits using an EPC building modeling tool given to us by Tyler Plett, one of our advisors. And it really stems from the idea that solar panels on the roof will decrease the amount of solar that reaches inside the building to heat the building. So as a result, in the chart, you can see that in the summer months, there's less cooling loads that you need, less energy you need to cool the building. But of course, in the winter, you need a bit more. So overall, we found with this preliminary analysis that 96,000 kilowatts of electricity can be saved in the summer months, and you get a total yearly thermal load decrease.
So now to look at the financial performance of the systems. All systems achieve a competitive IRR for the investor and positive customer savings. So that the output for the aggregate of the Auraria side systems is shown in the top chart here, and that comes out to almost $800,000 of savings over the 20-year contract period for the customer, and also an IRR of 8.6%, which is standard for projects of this scale. As for the Denver side, the PV system has a very strong investor return of 11.75% and a net present value of savings for the customer at about $35,000. Next slide. So one of the other challenges for this use case was addressing resiliency concerns for the science building. So the science building has about $1 million of perishable items inside. So even though this system technically has negative customer savings by including the battery, it actually provides significant value to the customer. So the system is designed to survive nearly 100% of 3-hour outages or shorter, with 3 hours being the average length of outages in Colorado. And the system also implements a peak shaving strategy to increase the value to the customer.
So now we'll talk a little bit about our system design approach. Matt, you're muted.
So for each of the rooftops, how can we best arrange the solar panels to meet each building demand? So in one case, you can lay them flat like this. That'll result in no shading loss, but there is a significant tilt loss because it's Denver. It is 39.8 degrees north of the equator. So you can tilt them to lower that tilt loss, but now you're shading the panels significantly. All right, so to get around that, you can space them further apart, but then you're not using that roof space as efficiently. So how can you balance all three of these variables to achieve a maximum power output, and how can we optimally design an array? Next slide, please. So what I did is I empirically modeled the energy output for every building as a function of tilt loss and shading loss, and I define functions for both the shading and tilt loss as a function of panel tilt and panel spacing. You can plug this into Excel solver and figure out the best way to arrange the panels. If we go to the next slide, the best way to arrange the panels really depends on your distribution impact analysis. All right, so for the convention center, if we want to maximize the energy production for a given roof space, you put the panels really close together and you only tilt them just slightly to significantly reduce your tilt loss, while also introducing only a small amount of shading. Whereas on Cherry Creek, a building that doesn't have a huge energy load, you can space them further apart to minimize those losses and to get more energy out of each panel. Next slide.
Right. So For the distribution system impact analysis, the goal really was to find at each location, how can we find the maximum system size without violating any of the voltage, overload, or net export constraints. In the interest of time, I won't go too much into it, but what we did was we did a manual route finding algorithm with this dotted line that represents the theoretical threshold of your PV system that would violate the export constraints or any of the other constraints. And what we did is we kind of started with an initial PV sizes based on the loads of the buildings, and then we the red dots represent a PV size that's too big, so we decrease it. If it's a black dot, it's fine. It doesn't violate any of the export constraints, so we can increase it. And then we want to get as close as possible to the dotted line. Then this final PV would be fed to Matt's optimization program to find the best PV layout. The next step would be an initial transformer sizing, considering full PV generation as exports onto the Auraria subgrid. But that's not realistic, because what we're looking at is a PV system that only exports the net exports because it is behind the meter system, represented by the green curve there. Finally, we did a battery analysis and a volt-var functionality analysis, where we found that there really is no benefit, even at the interval of greatest generation throughout the year. At the top left, there's base case PV. The bottom right is the most stringent volt-var, and there's really not enough of a difference or a benefit to justify spending more on smart inverter functionality.
So our process for sizing the battery came from trying to get a 100% survival rate of about the 3 hours. So the process that we took was we used Homer Grid to find what size was needed at specific high load times. Then more analysis was done to see the performance at longer outages. We also determined how much battery we need to do peak shaving efficiently. So we used these different sizes, ran it through Homer, and then found the benefit, the utility benefit of that, and then calculated a marginal benefit. And as seen from the graph, the marginal benefit becomes negative at about 250 kilowatt hours. So the final battery size and allocation is based off the addition of these two sizes with a minimum state of charge of about a 20% to increase battery longevity. Next slide. So the general process for our Auraria side financial analysis is we knew that we need to get the 8.6% IRR because that's a market-based value, and we need to make the project attractive to investors. So we used a Homer Grid to calculate the customer savings from the utility, and then put this in our financial model spreadsheet. Something we tried to optimize was the debt to equity ratio. And though we weren't able to get, an average like 70% due to constrained cash flow, we were able to have a really good IRR and customer savings. Next slide. So then the output is our PPA price and the customer savings, and it becomes net, or it breaks even after about 9 years. Next slide. So Denver side was pretty similar, except in this case, the PPA price is actually determined first from the discounts on the utility provided community solar credit rate. Next slide. And so then this gave us our really strong IRR of 11%. And as shown in the graph here, the system breaks even after about 5.5 years.
So we want to give a quick wrap up of our system and its benefits, and based on the proposed design using those rationale and approaches. So looking at clean energy generation, we get 3.6 gigawatts for Auraria and 1.3 gigawatts for Denver in the first year. We also have a competitive IRR and a positive 20-year net present value. We also looked at greenhouse gas emissions reductions using LCA calculations from NREL based on the generation profile of Xcel Energy, the utility. And we found that there's significant kilograms of CO2 offset, including their social cost of carbon with those dollar values. We also get good energy efficiency savings. And finally, we also help accomplish the Sustainable Campus Program's goals with the alternative transportation, with the EV charging ports that encourage electric vehicles, the food and gardens goal from the extra community garden on the Confluence rooftop, and an education and outreach goal is achieved through the education through the community garden on the Confluence rooftop. So we want to thank you all for your time, and wondering if you have any questions for us.